double integrals weren't enough of a pain, we now have triple integrals. You have an object, any object, so it's a three-dimensional shape, and we'll call it E. So you can think of I'm shading to give it depth. Let's put a 3D object D has a density that is variable. So it's not a homogeneous. It's not a homogeneous material, but its density varies from point to point. So if it's function rho of x, y, z, it indicates a density for any point in this object. So what is the mass? Well, we all know what the formula for mass is, right?
Density times volume?
Density times volume. Now, so if rho was a constant function, then the mass would just be that constant rho times the volume of this region. But first, we need to define what it means to compute the volume in this manner when we just have some general shape, general region in R3, how we compute the volume of that. And then we still need to be able to take into account what if rho is not a constant. If it's a variable density like this, we still want to be able to compute the mass. So what you can do is we can approximate E by several boxes. Small boxes that have dimensions delta x, delta y, and delta z. So the mass of this box is going to be approximated by the density evaluated at a certain point in the box, what I'll call x star, y star, z star, times the volume of a box, which in this case is simple, it's just delta x, delta y, delta z, and we'll call that delta v. So that'll be the volume of each one of these individual boxes. So that would mean that the mass can be approximated by a sum over all boxes, whichever ones you have, that approximate, that represent the entire region. And I'll call these boxes BI. I goes from 1 to up to n. That's the total number of boxes that you have. And then for an irregular region like this one, your box is not going to follow any particular pattern. You're just going to have however many it takes to approximate each portion of this blob. So you'll have, for each box, you'll pick a point in the box, any point, you'll evaluate the density at that point, and then you'll multiply this by the volume of that box. And we're assuming, just to keep things simple, that all of these boxes have the same volume. So now what you do is you let the number of boxes go to infinity, so delta x, delta y, delta z are all going to 0, and that gives you the exact mass of the object, a triple integral of the density. So So this is one of the most common applications of a triple integral is for computing mass. All right. And so the way we evaluate things, just like for double integrals, we would do an iterated integral with respect to, first with respect to x, then y, then z, or whatever ordering of the variables is most convenient. So the main difference between triple integrals and double integrals, besides the fact that you're doing one more integral, that doesn't really affect things all that much. You're still doing the same kind of anti-differentiation. The real challenge of triple integrals is the setup. So if you're given a region, region bounded by this plane, this surface, how do you get from that description to find the limits for all of your integrals in your iterated triple integral? That's going to be where the real work is done. Once you figure out what the limits are, then the work involved isn't really any different than doing a double integral. It just takes longer because you have 3 integrals to evaluate instead of 2. All right. Now, so we'll spend a lot of time going through some examples of how you would set up and then evaluate certain triple integrals. But before I get into that, I want to talk about a couple other uses for triple integrals. So given a solid E, again a three-dimensional object, where is its center of mass? Also known as its center of gravity. And we'll call that point x bar, y bar, z bar. All right. So the way you can figure that out is using triple integrals. So first, you compute the mass. It's going to be m. So that's just a triple integral of the density. All right. And then what you need are the moments of your solid of the x, y, and z axes. Right. So to compute these, sorry, not the axes. I'm thinking of 2 dimensions. We're on coordinate planes. So you have the xy plane, yz plane, and the xz plane. So if we draw such an object in three-dimensional space, x, y, z, so it's floating somewhere out here, and we want to compute the moment of this solid about the xy plane. So here's the xy plane here. We need to know at any point in the object what is the distance from that point to the xy plane. So if I have any point in this object, x, y, z, what's the distance from that point to the xy plane?
Would it just be z?
Yeah, it's a z.